In the last video, we had finished up developing the Maxwell equations. We have the two Gauss's laws. Gauss's law for electricity, remember, says that a way to make electric field lines is to have them start or stop on electric charges. Gauss's law for magnetism says there are no magnetic charges. So we can't have magnetic field lines starting or stopping on things. We also have Faraday's law. Which says that another way that we can make electric field lines is to have a time-varying magnetic flux. These electric field lines will be oriented like circles that close in on each other, so they don't start or stop on a charge. They just loop back on themselves. And then finally, we have the Ampere Maxwell Law. This says that there are two ways to make magnetic field lines. One way is we can have a current. Moving electric charges can make a magnetic field. The other way is we can have a time-varying electric field. In both cases, the magnetic field lines that we make will loop back on themselves. They won't start or stop on anything because there are no magnetic charges. Now, I want you to notice something here. And I admit here that I'm going to be kind of hand-wavy here. But look at this. If you see here, the electric field that we generate is, if we're not changing the area or the angle, would be proportional to the time rate of change of the magnetic field. So, very hand-wavy. This isn't 100% with all the I's dotted and T's crossed, but very hand-wavy. We can say that Faraday's law tells us that the electric field is proportional to minus dB dt. And again, not crossing all the I's, not dotting all the T's. If we don't have any moving charges at the moment, this bit right here of the Ampere Maxwell Law tells us that a magnetic field would be the magnetic field we make would be proportional to dE dt, to the time rate of change of the electric field. So you might not realize this, but this is actually looking kind of wavy. I can take it as far with this heuristic argument by at least looking at what underpins a mechanical wave, which is a simple harmonic oscillator. Remember, in mechanical waves, every point on the wave is undergoing simple harmonic motion. If we can at least see that there's some simple harmonic motion coming out of this, then at least there's some plausibility that this is a wave, and then I can work a little harder to argue for it. So let's look at that. So here, I'm going to draw boxes around my E's and circles around my B's, and let's change the color for that. And now I'm going to go and take a look. Whoops, sorry about that. Now I'm going to go take a look at a mass on a spring. So thinking back to introductory mechanics. So I've got myself a mass sitting on a spring, mass M, spring constant K. I go ahead and I displace it over. So it's currently saying some distance x. I let it go. We know that the force it feels, we know that the force it feels be equal to minus kx. Why the minus sign? Well, if I'm to the right of equilibrium, so this is my equilibrium position here. If I'm to the right of equilibrium, x is positive, but the force is to the left, so I need it to be negative. And if I'm to the left of equilibrium, x would be negative, but that's okay. I need the force to be pointing to the right then, and negative times negative is positive. So either way, the force would be always trying to restore it back to the equilibrium position. Okay, so we remember that F equals ma from Newton's second law. We can put in that the force here is minus kx is ma. Well, okay. So minus kx equals, well, let's go back to the definition of acceleration. We can say that that is dv dt, and then we can remember that v is equal to dx. Whoops, I ran off the edge. Pardon me one quick moment. We also remember that v is equal to dx dt. Now, take a look at this. Again, I'm going to draw the blue boxes around the x's. And the maroon circles around the v's. You can move the minus sign. We can multiply both sides here by -1 if we want. So let's just go and do that for the moment. So multiplying both sides of that equation by -1, that would still be true. Now look at this. Blue box is proportional, because we got some constants here, but it's proportional to minus the time derivative of maroon circle. And maroon circle is proportional to the time derivative of blue box. These are mathematically the same thing. So this is simple harmonic motion. We've got simple harmonic motion buried in the Maxwell equations. Now, remember, I'm arguing that this is going to give rise to an electromagnetic wave. So we still have some more work to do, but we remember that for any wave, with a mechanical wave, any point on a wave is undergoing simple harmonic motion. So that seems reasonable. So before we go on and check that, before we go on and do the hard work of deriving it, let's at least see if we're somewhat justified in that. And I'm going to appeal to experiment here. So this is an experiment due to Heinrich Hertz, as in the guy who eventually became the unit. So we talked about this before. You have an inductor that is just plain hooked up in series to a capacitor. And we can imagine having Scotty beam charges on the capacitor, and then we saw that the charges have to slosh back and forth in simple harmonic motion. And then we sat and thought about and realized that since nothing can run forever, there has to be a mechanism of loss. And that mechanism of loss is that this is actually making an electromagnetic wave. Now, what Hertz did to detect it is he basically made another capacitor and hooked it up to a very sensitive ammeter. And he saw that the ammeter needles, sure enough, oscillated back and forth in sync with the oscillation frequency of the LC oscillator. He wound up having to do a whole tour de force of experiments, though, because people weren't readily convinced that they're convinced that he saw something. In the literature for a while, they called them Hertzian waves. It took quite a while to show that, yes, these electromagnetic waves that he did had all the same properties as light, mostly because the wavelengths that he was making were thousands of times longer than visible light. And so it wasn't completely obvious to people at the time. But he showed that These things reflect the same way light does, they refract the same way light does. Basically, any trick that you can make light do, his longer wavelength electromagnetic waves did the same thing, and he showed that they propagate at a speed of somewhere around 1 over square root of epsilon naught mu naught. Now, if you go take those numbers and stick them into your calculator and grind it out, you're going to get that that's just a touch under 3 times 10 to the 8 meters per second. So we have experimental evidence that yes, indeed, light is an electromagnetic wave. So now let's go and think about how we actually generate them. Oops. There we go. So generating electromagnetic waves. And to do this right would be way beyond the scope of this course. But if there's one take home, the way you make any electromagnetic wave is you take a pile of charge and you shake it up and down. So that's how you make any electromagnetic wave at any wavelength. All right, now to do it right and to actually think about the charge moving up and down continuously, that would be a little rough for the level of math that we've got here. And it's not instructive, but we can at least think about this thought experiment. So we can think about an electric charge that I place right here. Let's make it positive just for sake of argument. And let's draw a few electric field lines for it. Okay. Missing one. There we go. So we can draw a few electric field lines for it. There. And then what we can imagine is that sometime later, we just plain teleport the charge here. So it was here, teleported to here. And so we just ignore the fact that in reality it would have to go from here to here all at once. All right, well, let's think about what those electric field lines would look like a long time later. A long time later, they would be radiating out like a porcupine from the new position. But here's the thing. On careful inspection of the Maxwell equations, what you realize is that information about the position of the charges. Remember, the field is a property of space itself. The position of information to space about the position of the charges can't propagate any faster than the speed of light. So say at some intermediate time, we can imagine that, say, right here, this bit of space got the memo that the charge had moved, but out over here, this bit of space still hadn't gotten the memo yet. And if that was the case, then the electric field would be pointing away from the old location. So I'm going to beg your indulgence here because the art is going to get really sketchy, but I'm going to try. So here's the old position. Drawing it in a dotted circle. There's my new position. Okay. And so what I'm going to do here is I'm going to draw in I think I want them a little closer to each other. Yeah, that's going to be better. All right, so what I'm going to do here is I'm going to draw in the electric field lines from the new position out to some point. So so here, trying to draw a circle. Okay, we're all just going to have to agree that that's kind of a circle. Sorry. So this is how far out how far out things have propagated, where space has gotten the memo that the charge is located here now. Out over here, it hasn't gotten the memo yet. So out over here, the electric field lines are going to be pointing directly away from the old location. What that means is that at this point right here, we can't have a disconnect. So instead, we have to have our electric field line, pardon me, I'm struggling for colors here. We have to have our electric field line join the old to the new. And this is happening in other places as well. I'll draw just a couple of lines in the interest of time. I won't try drawing a whole bunch. So we can try, say, this line here. So anywhere from here to here, space has gotten the memo that the charge is here. Past this point, space still hasn't gotten the memo yet, and as far as it knows, the charge is still located there. So out there, the electric field line would be looking something like that. And then in between, we have to connect the two. All right. Now here's the deal. Is right at this point, the electric field is changing radically. The direction has completely flat out changed. So since we're having a time-varying electric field here, this is going to have to induce a time-varying magnetic field. And then what's going to happen is that time-varying magnetic field will reinforce and make a time-varying electric field and so forth. The result you get looks something like this. So the red is the electric field vectors. Now, be careful here. Unlike other waves we've seen, here nothing is being displaced. These are all vectors that are associated with a specific point in space. But as we let it run, if we look at any particular location, we can see that we have a time-varying electric field, and at right angles to it, we end up having a time-varying magnetic field. Now that time-varying magnetic field in turn induces a time-varying electric field, again at right angles to it. And there is a definite way these things get oriented. So this is some more right-hand rule stuff. So using your right hand, make a three-fingered widget with your index finger pointing out, your bird finger pointing at right angles, your thumb pointing up like we've done before. Remember, when you take the idea is we're going to be taking a cross product here. And with the cross product, remember the first thing goes on the first finger, the second thing goes on the second finger. So first thing's first, second thing's second. Put the electric field on your index finger. At the same location, put the magnetic field on your middle finger. Your thumb will point in the direction of propagation, which is noted by C in the illustration. This is true whether you do it here or over here. So try it both ways. Pause the video for a second, play with it until you get it. Okay, so what we get is the direction of propagation points in the direction of E cross B. Okay, so we've at least argued that with our electromagnetic waves are transverse waves, although here nothing is being physically displaced. We have an electric and magnetic fields that are at right angles to each other, and I am going to try to draw it, and I'm just going to apologize right now. So here is my electric field. Now really nothing is being displaced. It's just that, say right here, the vector is pointing up to that amplitude point, or here the electric field at this location right here is pointing down and its strength is that much. But the strengths and directions of these electric field vectors are oscillating in are propagating in a very wave-like way. It's the exact same math for a wave we've seen before. And then at right angles going along for the ride will be our magnetic field. So here we are propagating our wave to the right. Okay, I warned you it wasn't going to look pretty. So, quick reminder on how waves work. The distance between two crests is still the wavelength, and the time it takes for an electric field vector to completely oscillate from up to down and back to up again is still the period, and the frequency is still 1 over the period. So with all of that, we can just plain take the exact same, since we have a wave equation, we can take the exact same wave result we had from our mechanics course, and we can write that the electric field vector will be equal to its amplitude, which I'll write as E naught, times the sine of 2 pi times x over lambda minus ft. And similarly, we can write an identical relation for the associated magnetic field. It'll be B naught times the sine of 2 pi x over lambda minus ft. And since this is a wave, just like any other wave, the speed of the wave, we always use c for the speed of light, will be equal to the frequency of the wave times the wavelength. Okay. Now, since the one field is inducing the other, and vice versa, we should expect that there be some sort of proportionality between the electric and the magnetic field strengths, and in fact there is. Where we can get that from is from Faraday's law of induction. Oops, sorry about all that. There we go. You can get that from Faraday's law of induction. Just remember that says, doggone it, integral E dot ds equals minus d phi b dt. Now, unfortunately here, I'm just plain going to have to assert that in a higher level math class, we can show that this implies that dE dx is equal to minus dB dt. All right, so we have our equations for the wave, so we can go ahead and stick each equation into each piece. So let's go ahead and do that. So we will have d dx of E naught sine of 2 pi x over lambda minus ft, and that will equal minus d dt. I'm going to need more room. That'll equal minus d dt of the expression in blue here, b naught sine 2 pi x over lambda minus ft. Alrighty. So if you go ahead and do all the derivatives, what are you going to get? Well, the derivative of sine is cosine, right? And so this is going to give me an E naught, derivative sine is cosine, so we're going to get a cosine of stuff. And then times the derivative of what's inside, we're just going to pick up a 2 pi over lambda as a result. That'll equal minus d dt. Oops, sorry, I'm taking the derivative. So it'll be minus, again, we'll have a b naught, leaving room in front. We're going to have cosine of stuff, and then I have to take the derivative of what's inside. I'm going to pick up a minus 2 pi f. So minus a minus there, 2 pi f. So the 2 pi's will cancel. The minuses all cancel. The cosines of things cancel. And I get that E naught over B naught, just cross multiplying here, is equal to f lambda. But since this is a wave, f lambda is equal to the speed of the wave. All right, so if that's true for the amplitude, it's true for the wave at any time, because they're both waving in mathematically identical ways. So if the ratio of the amplitudes is c, the ratio of the waves of the electric and magnetic field strengths at any time is the same. And so we get that the ratio of E to B is the speed of light. Now this leads to a practical consideration. It turns out that pretty much although it is possible to detect an electromagnetic wave using magnetic detectors, it's a lot harder. And this is because the speed of light being 3 times 10 to the 8 meters per second, what we get is that comparatively the electric field strength is comparatively higher. I know it doesn't make sense to do a direct comparison because the units aren't the same. But it's comparatively higher than the magnetic field strength. And so it turns out that the electric field is fairly easy to detect. The magnetic field is incredibly hard to detect. And so most detectors that we have, be it a CCD array in your camera, the chemical dyes in film, if you want to go old school that way, or the chemical dyes in your eyes, all of those are sensitive to the electric field. The magnetic field just sort of goes along for the ride, but we don't detect them. Okay. Is there anything else we can get out of this? And sure enough, there is. If we go and look at the Ampere Maxwell Law, so integral b dot ds is mu naught I plus epsilon naught mu naught d phi e dt. We're going to just assume that there are no currents in the area. So we're just going to set that equal to 0, just say absence of currents. So since ultimately these things all do get created by taking a pile of charge and shaking them up and down, we're saying that we're far enough away from the charges being shook up and down that we can just focus on the time-varying electric flux part of it. Again, I can use this, I'll make the same assertion that in a later math class, you can show that this implies dB dx is equal to, now here's a plus sign, so it's just epsilon naught mu naught dE dt. And again, you can make exactly the same substitutions you did before. So I'm just going to say make the same subs. And when you do that and you have your flurry of cancellation, you get another relationship for E naught over B naught. And that says equal to 1 over epsilon naught mu naught times, F lambda. Yes, I skipped an awful lot of algebra going from here to here, but you should try to work it out for yourself. But let's go and take a look at this. E naught over B naught, we worked that out. That's the speed of light. F lambda, that's a C there. Come on. F lambda, that's also the speed of light. Let's cross multiply. C squared is 1 over epsilon naught mu naught. If we go and take the square root of both sides, we get that the speed of light is equal to 1 over the square root of epsilon naught mu naught. Now, I want you to think about that for just a second. Let's go all the way back to the Maxwell equations just to stare at it for just a second here. So staring back at the staring back at the Maxwell equations, I have no idea what that is or why it's there. Okay. Staring back at the Maxwell equations, there's nothing in here at all that says who's doing the observing. These are laws of nature, and if we, there we go. That's really weird. What is up with that? And why won't it go away? Huh. All right, well, we'll worry about that later. So sorry. All right, so anyway, if we take a look at this, these are laws of nature. If we believe that every observer in the universe should have the same laws of nature, directly popping out of these laws of nature is that the speed of light is 1 over the square root of epsilon naught mu naught. Now, when we get to the unit on relativity, we'll explore two possibilities. One is that this actually only applied in for a very particular observer, but it turns out that you can show that you make good both astronomical and experimental arguments for why that is not the case. Or it is the case that everybody measures the same speed of light, leading to the thing I mentioned last time, where somebody can be driving along in their car or whatever at some very high fraction of the speed of light, and they can go and shine their flashlight, and the speed that they measure for the speed of light and the speed that you measure for that same light coming out of that same flashlight have to be the same. And like I alluded to last time, if it makes you feel any better, at least they'll disagree on the color of the light, so there's that. But they both will absolutely swear on a stack of physics books that the speed of light is 1 over the square root of epsilon naught mu naught coming out from that flashlight. This is going to lead to some crazy things. We're going to have to conclude, as we've already saw in the last class, that apparently different observers have different experiences of space. It turns out they also have to have different experiences of time to get everything to all square out. And also this fact that everybody measures the same speed of light. If you take that fact and you combine it with the Pythagorean theorem and you do some calculus for a little bit, you eventually get to E equals mc squared, the one physics equation that you probably knew before you ever took any physics, but you didn't know what it meant. But I'm getting ahead of myself there. That will be in a couple of classes. All right, so we're on the home stretch here. I just want to bring up a couple more results. So when describing the intensity of these waves, the way we usually describe the intensity is to use a thing called the pointing vector. The guy has to have the most amazing name possible. His name is Pointing. I'm not misspelling Pointing, that's the guy's name. But what the pointing vector does is it quite literally points in the direction of propagation of an electromagnetic wave. So, if this is my electric field vector, and this is my magnetic field vector, the pointing vector, what's a good color for pointing? There we go. No, that's not a good color. Orange. The pointing vector, S, is defined to be 1 over mu naught times E cross B. So again, go and convince yourself that that works out. So take your right hand, put the electric field on your index finger, put the B field on your bird finger. You should get the pointing vector pointing out on your thumb. That points in the direction of propagation, so the pointing vector really does point. Like I say, the guy had the most amazing name ever for what got named after him. And this also is the intensity, related to the intensity of the wave. So, since the electric and magnetic fields are always at right angles, we can also write that the magnitude of the pointing vector would just be EB over mu naught. And using what we had before about how E and B are related, we can say it goes as E squared over C mu naught, which, keep in mind, almost anything that detects electromagnetic waves detects the electric field side of the electromagnetic wave. So this is what you would actually typically measure. Okay, so the intensity of the wave, which is the power over the area, defined the same way we did it for sound waves back in mechanics, is the average value of the pointing vector. So that will be 1/2 of this. Why a half? It's because since it's going as the square of the electric field strength, we're going to be squaring sine. And it turns out that the average value of sine squared is a half. So it becomes a factor of a half. So 1/2, 1/2 c mu naught E naught squared, or if you prefer, c epsilon naught over 2 E naught squared. And that's, again, because you're detecting the electric field, you're probably more interested in the electric permittivity than you are the magnetic permeability. Okay. It also turns out that since light is a wave, if you remember with magnetic waves, they would transfer momentum. And same is true for our light wave. So I'm going to have a little quick pause and ponder kind of thing. Have you ever seen, like maybe your 5th grade teacher had one of these signs, or you saw one at a science museum gift store, something like that? It looks like an old style light bulb, except very importantly, it does not have a vacuum inside. It actually has air inside. And then there's this contraption of 4 vanes usually shaped like a diamond. You can see how well that's working out for me. There we go. Oops. Yeah, it's as good as I can get. And on one side, the vanes were painted black, and on the other side, they were painted white. And if you shined a light on them, what would happen is this vane contraption would start spinning around. However, the way it winds up spinning around here is that it'll spin like that. So the black side's chasing the white sides. Now, at the science museum or when your 4th or 5th grade teacher showed it to you, they probably said that this was a demonstration of radiation pressure, or at least there's a good chance of it. If they did, I'm going to say that it's actually wrong. Try to guess what it actually is. Pause on that for a second and I'll get back with you. Okay. It is not a demonstration of radiation pressure, and this is just because of the same deal that you had when we thought about what happens if you throw a lump of clay at a wall versus a super ball. Which one sees the bigger change in momentum? And the super ball had double the change in momentum because it reversed the sign of the momentum rather than merely coming to a stop. So so here we can write our radiation pressure, this F over A. So this turns out to be I over C. That's if it's absorbed. If it's reflected, then it's equal to 2 I over C. Because if it's reflected, then the electromagnetic wave had to reverse direction, so there's double the momentum transfer, which meant the electromagnetic wave was exerting double the force. So for actually a demonstration of radiation pressure, it would be spinning with white chasing black. Turns out what's happening is that because the black sides do a better job of absorbing, they do a better job of heating up, and they have to get rid of that heat somehow. And so what they wind up doing is heating up the air right in the area, and the reaction from the air that's energizing pushes the vanes in the what would be the wrong direction for radiation pressure. All right, I'll catch you in the next one. Have a good one.